In this section, we'll discuss the preparation of alcohols. This important chart shows the oxidation levels of different functional groups. Memorizing this chart helps you to understand the relationship between different functional groups. To the left side is the low oxidation level, and to the right side, high oxidation level. Alkane has the lowest oxidation level. An example is ethane. So all carbon hydrogen, no double bond, no triple bond, no electronegative atom, simply carbon hydrogen single bonds. All right, that's the lowest oxidation level. Now, in organic chemistry, when oxygen is added to a compound, the reaction is called oxidation reaction. So by replacing one hydrogen by oxygen, then we get alcohol. And this reaction is oxidation. And alcohol has a higher oxidation level than alkane. Not only oxygen, we can replace by chlorine. That's an alkyl halide. Okay, and this is also oxidation because chlorine is electronegative, just like oxygen. And nitrogen, that's amine. So amines, alkyl halide, ethers, alcohols, they all have one oxidation level higher than alkane. They are in the same oxidation level. Now, when you adding oxygen is equivalent to removing hydrogen. So when the alkane two hydrogens is removed, it will form a double bond. Okay, double bond is made by removing two hydrogen from alkane, and that is oxidation. So this is oxidation. Okay, on the opposite, if you add a hydrogen, remember adding hydrogen, that's a reduction, right? Double bond is reduced to alkane. So double bond has the same oxidation level as alcohols, ethers, alkyl halide, and amines. Okay, now in aldehyde, you have a CO double bond. CO double bond can be thought of as carbon connected to oxygen. Okay, because double bond means two bonds, and so like two oxygen. And two oxygen is a higher oxidation level than one oxygen alcohol. So aldehyde and ketones, they have the same oxidation level and a higher oxidation level than alcohols, ethers, aldehyde, amines. Alkyne has three bonds, triple bond. So three bonds is higher than two double bond, two bonds. Okay, so that's higher oxidation level. And then when we go to carboxylic acid, it has a double bond with another oxygen. So you can think about it as three oxygens. Okay, similarly, esters, three oxygen, and so even higher oxidation level. Here, CN triple bond. All right, N is electronegative, and so it's higher oxidation level than alkyne. Okay, so these are all the same oxidation levels. The highest oxidation level compound is the CO2. CO2 is carbon with two oxygen, but both are double bonds, and so it's as carbon connected to four oxygen. Similarly, carbon tetrachloride, 4 chlorine. That's the highest oxidation level. Okay, now understanding this chart helps you to know whether reaction go to oxidation or reduction. For example, if you want to make amine to nitrile, okay, then you know this is oxidation reaction, and then you need to know whether you need an oxidizing agent. Okay, similarly, if you go from ester to alcohol, that's a reduction reaction, and therefore you need to think about reducing reagent. And in this chapter, we're going to introduce some reducing reagent. Okay, this chapter is about alcohol. And in this section, we are going to introduce the ways to make it. And we can make alcohol from alkyl halide. And that's the same oxidation level. So the reaction is not oxidation reduction, but it's a substitution reaction. And we can also make alcohol from double bond. And that's, again, not oxidation reduction, but hydration. Okay, we'll go over those materials. And we can also make alcohol from aldehyde and the ketones. And that reaction is a reduction reaction. And we're going to introduce some reducing reagent, lithium aluminum hydride, sodium boron hydride. We can also make alcohol from carboxylic acid, okay, and some reducing reagent we're going to discuss. Okay, so that's this what this is about in this section. Alcohols can be made from alkyl halides. In chapter 11, you learned that a primary alcohol with a strong base undergo SN2 reaction to give alcohol. So the hydroxide attack carbon on the back of the leaving group and give you alcohol. And tertiary alkyl halide with weak base undergo SN1 reaction. So the leaving group leave forms carbocation, and then water attack give you alcohol. So if you forget about this material, go over chapter 11. Alcohols can also be prepared from double bond, as you learned in Organic 1. We went over this material in chapter 10. When you combine hydrogen peroxide followed by hydrogen peroxide, 2 steps, the product is alcohol that obeys anti-Markov-Nykov rule. When you combine mercury acetate followed by sodium boron hydride, again 2 steps, the product is an alcohol that follows Markov-Nykov rule. You can also simply add acid solution. As a catalyst, water adds to double bond. You get also Markov-Nykov product alcohol. But the third method is not as good as the second one, the oxymercuration demercuration process. And this is because the third process involves carbocation, which may have rearrangements. We just briefly went over the preparation of alcohol from alkyl halide and double bonds. And these reactions are substitution reactions and hydration reactions. Next, we're going to look at reactions involving ketones aldehyde or carboxylic acid esters that are higher oxidation levels. And these reactions are reduction reactions. Ketones aldehydes, they all contain CO double bond called the carbonyl group. For carbonyl to become an alcohol, 2 hydrogens need to be added. And the compounds that provide this hydrogen is called reducing agent. One simple possibility is sodium hydride. In sodium hydride, sodium is positive charge and hydrogen is negative with a lone pair electron. Okay, that's called hydride. All right, this is very different from most hydrogen in organic molecule. For example, in methanol, this is positive, partially positive, and this is negative. In water, again, this is positive and this is negative. But the sodium hydride, the hydrogen is negative, has a lone pair electron. So this hydride will react with this positive hydrogen and serves as a base. So sodium hydride is a very good base. Okay, whenever you have water or any weak acid, it will react. Okay, but it's not a good compound to react with ketones aldehyde to make alcohols, because this reaction is not an acid-base reaction. Here shows two most commonly used reducing reagent, sodium boron hydride, lithium aluminum hydride. Both formula contain 4 hydride, and therefore the formula already suggests they are hydride source. Now both boron and aluminum belong to group 3 elements, and they form 3 bonds, and there's a p orbital that is empty, that can accept the electron, and therefore boron and aluminum, they all called Lewis acid. They can accept electrons. So we mentioned in last slide sodium hydride. You have a hydride that has an anion, okay, with a sodium counter ion. This, if we combine boron with sodium hydride, this hydride will donate electron to boron. Boron empty p orbital forms sodium boron hydride. So that's the anion, sodium boron hydride. Okay, and so this boron hydride is a combination of boron and hydride, and you can think about this just a hydride source that can provide hydride. So compared to hydride, in sodium boron hydride, and this hydride is small and it likes to attack proton. Okay, so small hydride attack proton, but in sodium boron hydride, even though it's equivalent to a hydride because combined with boron, but the size is much bigger than hydride itself, and therefore this boron hydride anion doesn't like small proton. Instead, it likes a larger cation carbon, and therefore it's called a nucleophile. So boron hydride is much better nucleophile than hydride. Okay, because hydride is small, it likes proton. All right, and aluminum is even bigger. Okay, it's bigger than boron. So boron aluminum hydride is even a better nucleophile that attack a positive charged carbon even better. The conversion of a carbonyl compound to an alcohol involves 2 steps. The first step is hydride, which comes from sodium boron hydride or lithium aluminum hydride, attack the positive charged carbon, forms a alkoxide ion intermediate. The alkoxide ion intermediate with a negative charged oxygen is protonated in the second step by acidic water, forms final product alcohol. So an example here is a butanol, which has a CO double bond, is treated by 2 steps: sodium boron hydride in ethanol solution, followed by acid protonation. Okay, if you combine these 2 steps, the CO double bond becomes an alcohol. Okay, now let's draw the mechanism together. All right, it's extremely important you know how to draw reaction mechanism. All right, so grab a pen and a paper. All right, draw the mechanism of this particular reaction. So first draw butanol. Okay, so you have a CO double bond. Remember, the carbon here is a positive charge and the oxygen is negative charge. Okay, so keep that in mind. And draw hydride. Okay, so even though this gives you sodium boron hydride, but you know it has a boron hydride which serves as a hydride source. So this comes from that one. So just simply draw hydride with a lone pair electron. Okay, particularly draw the lone pair electron, and then draw an arrow to show. Okay, this arrow shows the lone pair electron flow between hydrogen and the carbon. Okay, remember the carbon is positive, hydride is negative, so negative hydride lone pair electron attack positive charge the carbon, forms a bond. At the same time, draw another arrow to show carbon-oxygen bond, the pi bond break. Why? Because carbon can only form 4 bonds. It already have 4 bonds in the molecule. If hydride attack the carbon, then another bond has to break, and that's the pi bond. Pi bond goes to oxygen. So the product is a epoxide intermediate. So you have a new carbon hydrogen bond, draw the carbon hydrogen bond, that's the formed from the first step, and also draw oxygen with 3 lone pair electron. Okay, in the reactants it has 2 lone pair. We didn't show, but it's there. But when the pi bond goes to oxygen, it forms 3 lone pair electron with a negative charge. Don't forget, it has a negative charge. Okay, so that's an epoxide ion intermediate that formed from the first step. All right. Now, second step is the protonation. Oxygen with a negative charge is not stable. But if we provide acidic water, in acidic water, it should have hydronium ion. Hydronium ion structure is here. Okay, it's oxygen with 3 hydrogen. The oxygen is a positive charge. Okay, and now you draw another arrow from, okay, note this arrow, from oxygen lone pair electron to this proton. Okay, because the bond, this hydrogen oxygen bond is polar. Oxygen is electron negative, so that pulls electron away from proton, so the hydrogen must be positive. Okay, and therefore the lone pair electron, which comes from the negative oxygen, flow to the hydrogen, forms an oxygen-hydrogen bond. Draw another one to show the oxygen-hydrogen bond break goes to the oxygen, and this will give you water, OH2, that's a water. Okay, the 2 electrons go to oxygen, so the oxygen becomes neutral. Okay, more importantly, the epoxide ion now have a hydrogen in it. That's the final product, alcohol. So 2 steps. All right, first step is the hydride attack. All right, forms epoxide. Second step is the protonation step, give you final product. So please try as many times as possible until you are confident that you can draw this mechanism. In the last slide, we showed an example of aldehyde reduction using sodium boron hydride as a reducing reagent. Ketones are similar. Sodium boron hydride also reduces ketone into alcohols. Now, if reactants involves carboxylic acid or ester as the functional group, then these 2 functional groups are higher oxidation level than ketones aldehyde. Okay, go back to the chart, shows oxidation level. You will see they have higher oxidation level and they require stronger reducing reagent, and you need to use lithium aluminum hydride. Sodium boron hydride does not work for carboxylic acid and esters. Okay, they need lithium aluminum hydride as a stronger reducing reagent. Another difference is that hydride attack twice on these 2 functional group, and in the product you see 2 blue hydrogen. They comes from the hydride, attack twice, and the red one, this hydrogen, they comes from the second step, protonation step. We're going to see the mechanism in the next slide. Let's draw the mechanism of ester reduction. Again, let's do it together. So grab a pen and a paper. All right. So note that molecule contains a CO double bond and OR, and that's an ester functional group. For ester reduction, we need a lithium aluminum hydride. Okay, LAH represents lithium aluminum hydride, followed by acid protonation, second step. So first, draw the molecule. All right, that's the ester, and draw hydride. Okay, show the lone pair electron with a negative charge, and then draw 2 arrows. One shows the lone pair electron goes to the carbonyl carbon, and then the pi bond break goes to the oxygen. All right, and that gives you a epoxide that is similar to the one we draw aldehyde reduction. Okay, so the oxygen has 3 lone pair electron with a negative charge. Okay, now here comes the difference. If it's aldehyde, so let's draw aldehyde. Aldehyde has a carbon-hydrogen bond. All right, so if hydride attack this carbonyl carbon, all right, what we get is a alkoxide with 2 hydrogen. So the carbon-hydrogen, carbon-hydrogen, these bonds are strong. They don't break. On the other hand, for ester, we have this bond, okay, OR. And this O, oxygen with carbon, this bond is weak. And under some condition, this can break. In other words, this is a living group, okay, it can live. So under this condition, this alkoxide, all right, it can reform to make a more stable intermediate. And therefore, here shows the mechanism. Okay, you draw 2 arrows. Okay, one, this arrow shows the lone pair electron of oxygen go to the carbon-oxygen bond. From single bond becomes a double bond. At the same time, carbon-oxygen bond break. So this arrow shows the carbon-oxygen bond break. The 2 electrons go to the oxygen, forms a alkoxide. Okay, so what you get is this aldehyde. So CO forms a double bond, and this hydrogen comes from the first hydride attack. Okay, so here is a aldehyde intermediate. All right, and that's the one we don't have for aldehyde reduction, but only ester. Okay, ester reduction you forms by reform. You form this aldehyde reduction. But remember, aldehyde is still can still be reduced, because remember in the solution you have lithium aluminum hydride, and lithium aluminum hydride can reduce aldehyde. So next you draw hydride. Okay, so this is not the end. All right, hydride attack, draw 2 arrows. Okay, and one goes to carbonyl carbon, the other goes to oxygen, forms alkoxide. All right, so now in this alkoxide you don't have a living group. So carbon hydrogen, carbon hydrogen, carbon carbon bond, these are strong bonds, they don't break. All right, so this intermediate alkoxide has to wait until you have acid that you can protonate. So last step is protonation. Again, you draw hydrogen ion, the lone pair electron for oxygen attack proton, the carbon hydrogen bond break, goes to oxygen, forms water, and finally you form the water. So from here to here, that's exactly the mechanism we draw for aldehyde reduction. So for ester reduction, hydride attack twice. Here one, the first step, and here again. Okay, so hydride, first step, hydride attack forms alkoxide, but the alkoxide first reform, form a more stable intermediate, that's aldehyde. And aldehyde under attack second time give you alkoxide, and then protonate. And so in the final product, 2 hydrogens comes from the hydride attack, and oxygen hydrogen comes from protonation. Practice. What carbonyl compounds would you reduce to obtain the following alcohols? In A, this alcohol is a secondary alcohol. From the mechanism, we learned that the hydrogen attached to oxygen comes from the protonation step, and the hydride attack the carbonyl carbon. So here, this hydrogen probably comes from hydride attack, and therefore the original compound must have a double bond here. And so that's the one, which is a ketone. Okay, so for secondary alcohol, it's probably a ketone. And for ketone reduction, we know that we can use sodium boron hydride, which is a weaker nucleophile, or lithium aluminum hydride also work. So both work for ketone for this case. So 2 steps. Okay, first step, sodium boron hydride, followed by second step, protonation step, give you the product. In B, the molecule is a primary alcohol, Again, the hydrogen attached to oxygen comes from protonation, and the hydrogen with this carbon comes from hydride attack. So the possible reactants is CO double bond with a hydrogen. That's an aldehyde. So that when hydride attack, okay, and then protonate, so you get CH2, so HH, and that's the CH2, and then OH, okay, that's the product, okay. So the primary alcohol comes from an aldehyde. On the other hand, we also learned that if it's ester reduction, the hydride attack twice, leaving group leave also give you a primary alcohol. So the reactants is also possible to be this ester. Okay, because this is a leaving group, so hydride attack, all right, leaving group leave, hydride attack twice, give you also CH2, and then protonate give you OH. So ester, okay, here it doesn't have to be OCH3, it can be OC2H5. So any carboxylic, it serves as a leaving group. And even OH, that's a carboxylic acid, also leaving group. So hydride attack twice. All right, so esters and carboxylic acid, the reduction also give you a primary alcohol. So for primary alcohol, there are more possibilities. It could be an aldehyde, could be an ester, or carboxylic acid. But for these two, carboxylic acid and ester, you need a stronger reducing reagent. So lithium aluminum hydride followed by protonation. If it's aldehyde, then both works. Either sodium boron hydride or lithium aluminum hydride works. We just showed that alcohols can be prepared from aldehyde ketones, carboxylic acid, and esters by reduction reaction using sodium boron hydride, lithium aluminum hydride. Next, we are going to show that alcohols can also be prepared by some of these functional groups using Grignard reagents. Grignard reagent is synthesized by mixing alkyl halide with magnesium metal. In Grignard reagent, the carbon is negative charged carbanion. The reaction also follows two steps. So Grignard reagent followed by acid protonation. And the product is also alcohol. There's a difference between Grignard reaction and hydride reduction. In hydride reduction, the product has hydrogen added to the carbon. But in Grignard reagent, it's the alkyl group, okay, that comes from the Grignard reagent. The mechanism of addition of Grignard reagent is similar to the hydride reduction reaction. The first step, instead of hydride, is the carbanion from Grignard reagents attack the carbonyl carbon, forms a carboxylic ion. And the next step is protonation, give you the final alcohol. And note that in the final product, there's an additional R group that comes from Grignard reagent. So the final product, alcohol, is a larger molecule compared to the reactant's carbonyl compound. So here is an example. The aldehyde followed by two steps, Grignard reagent and acid solution gives you an alcohol with a larger alkyl group. Okay, so this reaction, the molecule reduction by sodium boron hydride, we already showed the mechanism. But now let's draw the mechanism for Grignard reaction. Okay, so first draw the aldehyde and draw the carbanion. This carbanion comes from the Grignard. So note that the Grignard has a CH3CH2. It's this carbon, okay, that connect to magnesium, has a lone pair electron with a negative charge. Okay, so draw this carbanion and show the lone pair electron goes to the carbonyl carbon. So it's this carbon. Forms a carbon-carbon bond, and then another arrow shows the pi bond break goes to the oxygen, and that is the alkoxide intermediate. Okay, and the next step, can note that this intermediate has no leaving group. There's no leaving group, and therefore it has to wait for the protonation. So when the solution has hydrogen ion, okay, the draw an arrow. Show the lone pair electron goes to the proton, forms alcohol, and then another arrow shows the two electrons, the bond break, two electron goes to oxygen, forms water, and the final product is an alcohol with a ethyl group coming from the Grignard reagent. This is a comparison of hydride reduction and Grignard reaction. Both follows two steps. In hydride reduction, the first step is the hydride attack forms a alkoxide intermediate with a carbon-hydrogen bond. In Grignard reaction is the carbanion attack carbonyl carbon forms a alkoxide with a carbon-carbon bond. The next step is both are protonation, give you the alcohol. And so for hydride reaction, the final product has additional carbon-hydrogen bond, but for Grignard reagent is the carbon-carbon bond. So the product has additional alkyl group, comes from the Grignard reagent. Here shows some examples of Grignard reactions. In the first example, cyclohexane connect to the magnesium bromide. So this carbon is a carbanion with a lone pair electron and a negative charge. So the lone pair electron of this carbon attack the formaldehyde carbonyl carbon, forms a alkoxide, and then protonation give you a primary alcohol. In the second example, benzene carbon is a carbanion, and this carbanion lone pair electron attack a aldehyde, forms a alkoxide, protonation, and that give you a secondary alcohol, because in aldehyde the carbonyl carbon already have one carbon. So if Grignard attack, you have two, so this carbon now connect to two carbon, and therefore this is a secondary alcohol. In the third example, this ethyl group is a carbanion. So carbanion carbon, this carbon attack this ketone. All right. Note that in ketone, this carbonyl carbon already attached to two carbon. So when you add another one by Grignard reagent, you have three carbon connect to this carbonyl carbon. So now this alcohol is a tertiary alcohol. Grignard reagent also react with esters. Remember, when esters react with hydride, hydride will attack twice. So hydride attack carbonyl carbon, forms a alkoxide, and then alkoxide reform leaving group leave forms an aldehyde. So second hydride attack, followed by protonation, give you the alcohol. If the ester combine with Grignard reagent, the Grignard reagent carbanion also attack twice, because here serves as a leaving group. So the final product is a tertiary alcohol, because two alkyl groups are added to the product. Now, although carboxylic acid also react with hydride, okay, two of them attack forms a alcohol, the carboxylic acid does not react with Grignard reagent. So this doesn't react. The reason is Grignard reagent is a base. Carbanion is a strong base, and the carboxylic acid has a proton as an acid. So the two will react as an acid-base reaction instead of nucleophilic addition reaction. Here shows an example. An ester undergoes two steps. First, react with Grignard reagent. Second, with acid solution, give you the final product, a tertiary alcohol. Well, this is a leaving group, and the 2 alkyl groups added. These 2 alkyl groups comes from the Grignard reagent. In this case, it's 2 methyl groups. Now let's draw the mechanism of this reaction. So first, draw the ester. Okay, draw carbanion. In this case, 1 carbon, okay, CH3 with a lone pair electron, negative charge. Okay, note this comes from Grignard reagent. And draw 2 arrows. Okay, one shows the lone pair electron goes to the carbonyl carbon, forms a new carbon-carbon bond. And the second one shows pi bond break, goes to oxygen, forms a carboxylic intermediate. All right, so note you have a new carbon-carbon bond. But also notice that here you have a leaving group. So this a carboxylic intermediate will try to reform. Okay, so 2 arrows. One shows the lone pair electron of oxygen come back, forms a pi bond, and the other shows carbon-oxygen bond break. 2 electron goes to oxygen, and this is the intermediate. It's a ketone. So ketone here is the intermediate. This method comes from Grignard reagent. Now this is not the end, because ketone can still react with Grignard reagent. So a second carbanion from Grignard reagent will attack carbonyl carbon, forms another carbon-carbon bond, and the carbon-oxygen bond break forms a carboxylic. So now you see 2 methyl groups comes from the Grignard reagent. All right, this carboxylic, there's no leaving group, so it has to wait for the protonation step. If the solution has hydrogen ion, then oxygen protonate give you the final product, where 2 methyls come from the Grignard reagent, and hydrogen comes from protonation step. Remember, in Grignard reagent, the carbanion is a strong base. If the reactant contains acidic hydrogen, the reaction will undergo acid-base reaction instead of nucleophilic addition reactions. Okay, so the functional group contain acidic hydrogen include alcohol, amine, thiol, carboxylic acid. Practice. How could you use the addition of Grignard reagent to a ketone to synthesize 2-phenyl 2-butanol? Now remember, in Grignard reaction, carbanion attacked ketone to form alcohol, and the final product has an extra alkyl group, comes from the Grignard reagent. So in this final alcohol, and this may come from the Grignard reagent. If that's the case, then the ketone is this one. So that's the ketone, and the Grignard will have 2 carbons. So that's the Grignard carbanion attack this carbon, and a carboxylic protonation, and that will give you the product. Now this method may also come from Grignard reagent. If that's the case, then the ketone should have 2 carbon ethyl group here, and then the Grignard will be methyl group. So that will carbanion attack, give you the final product. But the benzene may also come from Grignard reagent, and then if that's the case, then the ketone will be methyl ethyl ketone. So the benzene as a carbanion will attack this ketone and give you the product. Practice. How could you use the reaction of Grignard reagent with a carbonyl compound to synthesize 2-methyl 2-pentanol? Now, just like the last question, we can assume any of these substituents as coming from Grignard reagent. For example, we can assume methyl comes from Grignard reagent. Then the ketone must be propyl methyl ketone. So that's the reactants, and the methyl comes from Grignard reagent. We can also assume this propyl comes from Grignard reagent. Then the ketone will be dimethyl ketone. So this is the reactants, and the propyl comes from Grignard reagent. All right. Now we also learned that Grignard reagent can attack twice to the carbonyl compound if it has a leaving group in ester. So the third method is that we have an ester, okay, the ester will have a propyl, and this is a leaving group, and this can be a methoxide or ethoxide, so any leaving group, all right? And a Grignard reagent is a methyl, so it attack twice, give you 2 methyl with a propyl alcohol. In summary, alcohols can be synthesized from alkyl halide by substitution reaction or by double bond through hydration reactions. Alcohols can be made by reduction reaction from ketones aldehydes, and the reducing reagents are lithium aluminum hydride, sodium boron hydride. Both works. Now, if we use Grignard reagent, the alcohol will have an extra alkyl group comes from Grignard reagent. Alcohol can be produced by carboxylic acid and esters using lithium aluminum hydride, not sodium boron hydride, because these are higher oxidation level. They require stronger reducing reagent, lithium aluminum hydride. If we use Grignard reagent, it will attack twice, and leaving group leave, and this is only for esters. Okay, for carboxylic acid, Grignard reagent does not work. Homework: please work on problem 17.6 to 17.11.